we will start. In the last class, I gave a definition of determinant. However, today's our goal is understanding some property of determinants. I will give the definition again. We construct the determinants by constructing cofactor, and we expanded it inductively. We say that cofactor expansion. So, to understand this, we define what is cofactor, and cofactor was alternated minor, and the minor was determinant of lower submatrix. So we define it from 1 by 1 matrix, and it is square matrix, so it might be natural to define from square matrix. So let A be a square matrix, and determinant was alternating sum of minors of the sum. So we define it from the we defined it inductively, so we will assume we know the lower levels determinant how we get. So if we determinant of the minor, the submatrix, and let me it Mij, and it is a submatrix after removing ith row and jth column. Or deleted, removed from A is called it minor of entry Aij. Sometimes I will wrote large A because the matrix we denoted the matrix as A. So in my notes, maybe it is small a. However, in this class, I will use large A. Oh. And we constructed the determinant as a alternating sum of minors, so I think it is more convenient to define determinants. So we will multiply the minus 1 to the I plus j, and it is called the cofactor. And we defined it. We showed that if we define the determinant as sum of a column or row, and if you choose ith row, then it is the sum of minus 1 to the I plus j, aij, and determinant it is minor mij, and I will denote it again as a bar, determinant of a bar of ij, and a bar is removed submatrix of A. So I will read it by j. Like this. So it is mij, and this means if you choose ith row, then first you will remove this column and row, and the submatrix will be like this. Submatrix is composed from these two vectors, and it is lower dimension of matrix than A's dimension, so we can get the determinant of A bar 1 of I1. So we will move this term 2, 3, 4, and to n if it was n by n matrix. So and we showed that if you choose j's column, then you can do same things by constructing the submatrix. It will be give n minus 1 times n minus 1 matrix, and we get the A1j bar determinants, and it will be we defined it inductively, so it makes sense. And all summation of this, I explain how we choose in this matrix. And when we choose it, we will choose only one entries in one row, and we will choose one entries in one column, because by constructing like this, we removed this line if we choose this. So it is there are n factorials combination of this choice, and this summation and this determinant will be given n factorials convenient, so it does not depend where you choose. So it is well defined, the determinant. And from this definition, we can see the next theorem naturally. If A is a matrix, a square matrix, and it has 0 row or 0 column, then determinant of A will be 0, because we will multiply the entry of Aij's column or row, one row. So if all entry of in row was 0, then the entry in summation is all 0, so the determinant will be 0. And it is remarked, and we see a kind of special matrices. It was triangular matrix, and the triangular matrix case lower. Of course, it can be upper triangular. Matrix A, its determinant is equal to the product of the main diagonal entries. It is also quite simple, because let's imagine the lower matrix. When you imagine this, and you can choose the first row or last column. I will choose first row, and then it's removed. Matrix is n-1 times n-1 submatrix, and it is also lower matrix. And by choosing the first row in submatrix, and then we will get lower matrix again and again. And another entry is all 0. So in the summation of this, it will be remain just first vector or first vector, and so finally we only choose the main diagonal entries only, and we will product the entries as the determinant of the submatrix. So it is true. The remark is true. And also the upper triangular matrix case, also by choosing first column or last row. First column or last row, we can do we can get the same solution same results by the determinant is the product of main diagonal entries, and it is also from this we might think the transposition, because the transpose of lower matrix is upper triangular matrix, and actually transpose does not verb does not var wait, I will say again. The transpose is not invariant the value of determinant. Let me write again. Let A be a square matrix. That means the determinant of A is equal to determinant of A transpose, and its proof is also simple because we didn't depend on the choose of row and column. So by changing, when we get the result of the determinant in lower triangular matrix, we choose the first row, and when we get the determinant of upper triangular matrix, we choose first column. So it is just change of row to column, and it does not depend on the choice row or column or what row. So it makes sense. And we maybe if you see my previous lecture notes from 1 to 3 class, first and third class, then we learned to elementary row operation and its elementary matrix. So I will explain the determinant of elementary matrix. Actually, I will explain more generalized case. Let be a matrix the result and single color of A I will use row A is multiplied by scalar K. That means if you have a matrix A, and when you choose ith row, and you will multiply the ith row K, and it was saying the row operation. One K 1 1, and by you it was not. Wait, is it right? We will calculate it column and row, and then if you calculate this, you can get the case multiplied with matrix A to the row i's, and its determinant is K multiplied of determinant of A. And it is quite easy to choose the line ith row. Then it's at B ij's entry is same k a ij, and another minor matrix is minor determinant minor value is same to a's minor value, so it is just k summation the k a ij determinant aij a bar ij, and it is same determinant b bar ij, and it is b ij, so that means it's determinant of b. And also we defined it another row, elementary row operation, and second one is interchanging two rows, and its elementary matrix is this form. A. Oh, it is no. It is A. So in this case, I will write simply from A. Then its determinant is determinant of B is equal to minus determinant of A. Its proof is quite long. However, I wrote in my lecture notes quite long. However, if I explain it, its matrix is changed from A, and if we consider the ith row and kth row has changed, and the changed matrix is B. And we will choose the row of i's in B. Then inductively, if in the 2 by 2 matrix in the 3 by 3 matrix case, we will when we changed the rows, even row and even row, to change even row and even row, or there are two cases. One is each two even row interchanging, and of course all the row is also, I will see same case. And another case is changing even and odd row. So in this case, we will odd row and first two odd rows interchanging. Then there, from 3 by 3 matrix, it will happen, and we will, if we choose first and third row, then when we choose the first row, its minor matrix will be changed from A the upper side and below side, because in A matrix, when we choose the ith row, the first row in B is same to the third row in A. We interchanged the line. So if we choose the first minor of 3 1 entries, then it is A11, A12, A13, A21, A22, A23. Then its minor is A12, A13, A22, A23. However, in this case, if you choose the first entries, then it is 3 1, 3 2. Right. You choose 3 1, 3 2, 3 3, and 3 1, 3 2, 3 3. Okay. 2 1, 2 2, 2 3, 1 1, 1 2, 1 3. And when we choose the first row, then it will be removed the first row and first column firstly, and its minor is A22, A23, A12, A13, and it is changed of the matrix of A is minor. Like this. And we know the determinant of this is A12, A21 minus A13, A22. However, this determinant is A22, A13 minus A23, A12. So it has the opposite sign from A. And inductively, when you get the high-dimensional matrix, finally you will remove the rows to 2 by 2 matrix, and so the determinant was the determinant of removed matrix. The determinant of matrix will be multiplied to the determinant of A or B, and its sign has been changed, so it will be given the change the determinants to A from A. Papa is weak. I use this one. And the interchanging of even and odd row. In this case, we can see more easily. The changing even to between the interchanging between even row and odd row, then it's A11, A21, A1n, A2n, then it will be A21, A11, A2n, A1n. And if you choose the first row in A, then to compare it, we will choose second row in B, and it's I didn't. The determinant has the change of the choosing alternating sum. It was alternating sum, and it is needed. The alternating sum is choiced by how many row and column where the row and column, and it is changed even to it has changed odd to even rows, so its alternating sum will be give change of sign, and the entry is same to A, B when we choose the second and first row, and the minor matrix is just removing this line, and it does not change the minor matrix or the order of minor matrix. So the determinant of A bar ij is same to B bar ij. It is just change of one even to odd rows, so it has not changed the sign of determinants, the minor and entry of A and entry of B. So it just have its changing will be happen to the alternating sum from alternating sum. So all two cases we can see the change of sign of determinant. It means the determinant of B is equal to minus determinant of A. And the third case is the multiplying to another row, the multiplying and adding to another row. The final I will use blue one. There's no black marker. And the third one is there is A row and J column, and by multiplying scalar k to I from J's row, and by summation it, we can it is also a kind of elementary row operation, and it is same to 1 k 1 1, and by multiplying this, it is A, it is interchanged A. And in this case, we will calculate the determinant of B. Multiplying A is B. The determinant B is, when we choose the ith row, it is J equal 1 to N, I plus J, alternating sum of B, Bij, and determinant B bar Ij. It is the removed submatrix I row and J's column. And when we see the entries Bij, it is sum of Aij and plus the J's is not good. The notation was not good. So I will change the color. I use L because I use the J as the column, and so it is same to Lj of Lj entries of B matrix. It is also can be said A matrix. A's ij entries and determinant b bar ij, and it is the summation, so we will use the distribution rule, and it will give aij determinant b bar ij. However, it is removed just this line, so it is same to determinant of aij, a bar ij, and also k alj determinant of b bar ij, and in this case we can consider this inputting the jth row to a matrix, then it will be given the matrix 2jth row, and when you calculate the minor of determinant of this matrix, I will try to calculate. When you choose first row, I will explain again. Sorry for confusing. The determinant of b bar ij is removed. Aj multiplied the determinant of b bar ij means the determinant of the summation means determinant of having two j's, okay, two j's a matrix. From a matrix, we interchange the a to k, k multiplied with j's row, and when you choose another rows inductively, then it will give the minor matrix, and we will choose except these two lines. Then the final determinant is k multiplied with the jth row, j1, I will another notation, jl1, jl2, and another the jth row gives ajl1 and ajl2, and this matrix is determinant is ajl1 ajl2 multiplied with k minus this line ajl2 ajl1 is multiplied with, so it is 0. So the minor matrix, if you calculate it inductively to 2 by 2 matrix, then we can get the solution of determinant is 0. So it will be removed as the 0. Finally, it is same to the first term, and it was aij determinant a bar ij, and it is same to determinant of a. So we can see that if you adding to the multiplied j's row, multiplied with k, to multiply the k to ith row, then the matrix, the determinant of the matrix B is equal to determinant of matrix A. In this proof, in this probe, you see the distribution of determinants, and so you might think, is it possible to does determinants preserve the addition? However, the question is wrong. Remark. That means determinant A plus determinant B does not mean determinant A plus B. We see the matrix A plus B. In this case, it has same entries except ith row. In this case, it will be written determinant. The new matrix is A matrix is original matrix, and B matrix is multiplied matrix, and I will define the another matrix. C is just it is not added, it is changed to K multiplied the Jth row from A. So in this, by using this, then the determinant A, wait. Right, okay. So that A and B square matrix. Then the determinant A plus determinant B is happen. I think my notes, I mistake in my notes. When the two matrices share same entries, there is no markup. I will use red one. It share two matrices share same entries except the a single row or column. That means it means it is divided to matrix. The matrix B is equal to matrix A plus just only have entries, one rows, or this row is Jth row of A, or column. So in this case, the determinant will be in this case the determinant will be one matrix. It is not from A. Let me explain, okay? if the matrix share same entries except one lines, then it will be written. Oh, I will write it this. It is a matrix summation A and ith row, and if I define the matrix C, and I will define the matrix C is shared to another entries to this, to 0 entries, then in this case, 0 matrix is C, and interchange the two shared matrices C prime, and determinant B is equal to determinant of A plus determinant of C, and B is A plus determinant of C prime. B is A plus C. So usually, in generally, it does not make sense. It is not true. I will give an example for that. Before to give example, I will explain from this corollary. We calculate the elementary rows, and it was first one was multiplying to ith row, and second one interchanging two rows, and the final one is multiplied to another rows. So these elementary matrix the elementary matrix E resulted multiplying a row of identity. So it means it is elementary matrix, and it is the first elementary matrix. Its determinant is K of multiplying K or I, and the second elementary matrix is resulted from interchanging two rows, then determinant E is minus determinant E. The final one is resulted, if E is resulted from a multiply of one row of I to another, then the determinant of E is what we calculated. It does not change, because having same two rows or multiplied rows, it divided the two determinants A and B prime, and the B prime's determinant was 0, so it is same to original matrix's determinant. And the determinant of identity was 1, because it has main diagonal entries only as 1, and the diagonal matrix is also row triangular, and upper triangular, and its determinant was the multiple of main diagonal entries. And from this sense, the determinant of identity matrix is 1, so the determinant of E is also 1. So let me give some example for them. For elementary matrices determinant. First one is just multiply it to a line, to a row, and its determinant is 3. We sometimes use this notation. It is equal to determinant of this matrix. And if we change to line, first and last row, then its determinant is -1. And also finally, the third one means if you calculate the determinant of multiplying to another row, adding to another row, then its determinant does not change to identity matrix, from identity matrix. And also, we see this elementary operation to matrix, an arbitrary matrix. So the third one means if you have the matrix this form's matrix, then its determinant is 0. And actually, if you calculate it, -1 dot a minus 4 dot -2, then it is 0. -8 minus 8, so it will give 0. And actually, it makes sense more larger size of matrix. Matrix of larger size. If it has same scared column, then it is also its determinant also 0. So by using this property, we can get the determinants from the decompose of elementary row operations. If I do spoiler, then we see that the invertible matrix will be composed of only elementary matrices, multiplication of elementary matrices. So, in the case, these elementary matrix is determinant. There is no 0, so determinant map might give the information of invertibility of matrix. As the next chapter, we will see the some property of determinants. and Kramer's rule. It is the generalized to the third one to the matrix, and from this we will get the solution of linear system. And we see the first as the first example. The determinant does not preserve the addition. So, as the example, if you choose two matrices, one is 1, 2, 2, 5, and B is 3, 1, 1, 3, then A plus B is 4, 3, 3, 8. However, if you calculate the determinant A, then it is 5 minus 4, 1, and determinant B is 9 minus 1, so 8. However, the determinant of A plus B is 32 minus 9, 23. So it does not same. In general, it does not equal. However, the multiplication case, we can see a property, because when we multiply the one row or column by multiplying k, then it will be given the determinant when we denote change the matrix as B. Then the determinant of B was equal to determinant of A multiplied with K. So if you multiply K to matrix A, for any scalar K, the determinant Ka is, it has n rows, so it will give the k to the n determinant of A. You can get this solution from this easily. And we see we saw the results. The determinant was composite. The elementary matrix's determinant also has same property. For example, we see for any matrices to operate some elementary row operation, then it will give same result. That means when we define E is elementary matrix, then A is n times n matrix. Then the determinant of E times A, it is matrix multiplication, was same E determinant of A. we checked the result in the previous chapter, previous section. From this consideration, we can get the result by repeating application of that process. We might obtain determinants E1. In this case, E1 to ER is all elementary matrix times B is equal to determinant of E1, determinant of E2, determinant of ER, and determinant of B. So from this remark, we can get the results. The invertible matrix will be formed as only elementary matrices multiplicated from elementary matrices. So it is the mean invertible matrix. It cannot be zero. All determinant was not zero, but one was k multiplied determinant, and second just changed the sign, and third one was just same determinant, having same determinant. So by multiplying this operator, it will give non-zero. We consider the state ones of remark. We might be able to generalize the remark as any matrix, any true matrix, or square matrices of same size. And then determinant AB is it preserves the multiplication as scalar multiplication and matrix multiplication. It is quite simple because wait. I just wrote invertible matrix case. Okay. When A is 1, I will choose one matrix. Then, if A was invertible, then AB is also invertible, and invertible matrix will have determinant 0. Am I explained? I skipped the back of that. if we give invertible matrix, then it will be the determinant will be non-zero. Then that means the determinant was 0, and it was not invertible matrix. And I will think a little. I will explain one thing okay, before to prove this. Let A be not invertible square matrix. Then determinant of A is 0. If we have seen the property of invertibility, and if it can be written, if A was invertible, then its reduced row echelon form is identity. A is invertible. If and only if the reduced row echelon form is identity matrix, and this means if at A is not invertible, then the reduced echelon form is not identity. So if we calculate it, the reduced echelon form is made it to be, it is reduced echelon form. Row. Then it is not identity, and it has only leading 1 and another 0 entries. And this form is also upper triangular, and so finally its determinant will be the multiplication of the main diagonal entries. However, it is not identity, so it has an elements, an entry which is 0, so the determinant of B it means 0. So from the previous fact, determinant A was equal to each determinant elementary matrices determinant multiplication of R1 and B. However, its value was 0, so that means the determinant of A is 0. So if the matrix A is not invertible, then the determinant of A is 0. So I will use the fact that from this to this theorem. So let A be not invertible, then its determinant is 0, and also if A is not invertible, then A matrix multiplication B is also not invertible, so its determinant is 0, so its equality makes sense, is satisfied. So we will see the case. Assume Here is the case. A is invertible. Then it means it will be written as the element of the multiplication of elementary matrices. So that means A is E1 product to ER. So the determinant AB will be given E1 to ERB, and the elementary matrix's determinant can be divided. The determinant preserve the matrix multiplication of elementary matrix. So it is same to for each determinant multiplication, and we calculate this only elementary matrices first, then it is same determinant of A, and remaining is determinant of B. So we get the fact determinant of AB is same to determinant of A, multiplication determinant multiplied is determinant of B. And by using this, we can get the one corollary. When we enter this section, I said the invertibility, the determinant will give the information of invertibility, and actually, if the matrix was invertible, then its determinant is non-zero. It has if and only if condition. And also, if A is invertible, then the inverse determinant will be determinant A, 1 over determinant A. It is simple because determinant of identity is same to determinant of A inverse, and by using these facts, it will be preserved. Determinant will preserve the multiplication, and then it gives the fact the inverse matrix is determinant is same to 1 over determinant of A. And then we return to the construction of determinant. It is a linear combination of entries of A and the minor matrix, minor value of remove the submatrix from ith row j's column. And this form, in the last class, we said we will. I mentioned it will be called it Cij, and then it can be written as a form linear combination. And so if we construct the matrix of cofactor, then it might be easy to get the determinants. Or systemically, we get the determinants. And it is called the adjoint matrix. So, adjoint matrix is I miswrite to my lecture notes. Let A be an n by n matrix, and let Cij be the cofactor of Aij. This is an entry of I through j's column. Then the matrix C11, I'll use same notation in my lecture notes. C1n, C2n, Cnn transpose it is needed because we multiply the same row and same column. So by performing transpose, we might construct A. It's called the adjoint matrix. And it is written adjoint of A. Its diagonal matrix, diagonal entries will be determinant of A. Because its transpose is, I will write adjoint of first. Adjoint of A times A. Then it is multiply C11, A11, and C21, A21. So A N1, Cn1, and it means the determinant of A. So let me give an example. For adjoint matrix, maybe I will not calculate in this class, and I will give as one homework. For a matrix A, 2, 2, 6, minus 4, minus 1, 3, 0. It is 3 by 3 matrix, and so the adjoint matrix's entries will be the determinant of 2 by 2 minors. The adjoint matrix of A will be 12, 6, minus 16, 4, 2, 16, 12, minus 10, 16. And I will find the first entries. It will be the minor removed the first row and first column, and then the minor matrix is 6, 3, minus 4, 0. Then the determinant is 6 times 0 minus 3 times minus 4, and it's 12. So its first entry is 12, and the second entry is remove the, it is transposed matrix, so two second row and first column, and its entry will become from the cofactor 2 minus 1. 2 minus 1 minus 4, 0. So minus 1 minus 4 as it is equal to 4, and this entry is 4. So by using this system, you can get the cofactor matrix as it is called the adjoint matrix. And we see that if you calculate adjoint matrix of A matrix multiplication, A is its main diagonal entries, it was determinant of A, and we will see the another parts of entries. Let A be on n by n matrix, and C be on C be the adjoint matrix of A. That means C is adjoint of A. Then the determinant, not determinant, its matrix multiplication is A, I, J, C, J, K. It is ith row, j's columns entry. It is equal to, it was determinant A when I equal to K, and another case it will be 0. To calculate it, we construct a special matrix from matrix A, and when we see the see matrix 2. I's column and case ith row and case column. When we matrix multiplication this line, I will assume case bigger than I. Actually, if you choose conversely, by doing same by following same proving, then you can get the converse. The bigger, in the case bigger I bigger than K, case also get the solution. So I will assume K is bigger than I. Then by interchanging to the ith row to case row to A, then it's otherwise can be seen to the determinants of the change in the matrix will be I will say matrix B, then determinant of B is same to with this ij entries, ikj entries, and ij ijk. I will give an example. So by giving example, it will help the explanation. One, three, two, four, two, three. If let A is 3 by 3 matrix, and I should find the other joint matrix. Let there is other joint matrix. Then when we choose I is 2 and K is 3, then when we calculate 3, this means second row and first column will be calculated first column, third row. So by constructing B, I will use A prime. It is depend on A. 2, 1, 3, 3, 2, 4, 3, 2, 4. It is changed to ith row to kth row. Then by multiplying matrix C, it's ik entries is the determinant of will be A prime C's determinant, because its determinant is the linear combination of these summation of these three and for these three entries, and the minor is when we choose this line, its minor is same to this minor. And we saw that the fact it is but it is same. It is equal to determinant of A prime matrix scalar multiplication determinant of C. And so we can see that we can say that determinant of when I is not equal to K, the summation J is equal 1 to N A Ij Cjk is equal to determinant A prime C, and it was determinant A, determinant C, and we will focus on the matrix A prime. A prime has same column, and the elementary row, the third elementary row stayed. If it has proportion of each of one row, like this form, then its determinant is 0, because by choosing another rows and by choosing another row, then it will give the 2 by 2 minors finally, and the 2 by 2 minor determinant is only always will be 0. So the determinant of A prime will be 0. So when I is not equal to k, in this case the value of summation is 0. So as the corollary, the adjoint matrix multiplication to A is determinant of A scalar multiplication to identity matrix. So from this, if the determinant of A when the determinant of A is not equal to 0, that means A is invertible, then in particular A is invertible, then the inverse matrix is determinant of A adjoint matrix of A. We get the result from this by dividing determinants and determinants A adjoint matrix A and it is equal to identity, and by multiplying the inverse matrix we get the fact the inverse matrix is same to determinant of A 1 over determinant of A matrix scalar multiplication to adjoint matrix A. I will use 10 minutes more. These adjoints, when we prove the facts, the non-main diagonal entries is all 0, we calculate the determinant A prime matrix multiplication C, and we will use this sense to get the solution of a linear system. So let A 지금 세미나 하고 있어. Let AX equal B be a linear system. N linear system. Then and also A is invertible. That means it has exact one solution. The linear system has exact one solution. Then the solution is when we write x is x1 to xn. x1 is determinant a1 over determinant a. a1 is has changed the first column to B vector, and another one is same to shared to A matrix. So in this sense, the AXN entries is same determinant of AN over determinant of A. I wrote the detail proof in my lecture notes, so I will use quickly. Since A is invertible, so we can have the invertible matrix. So X will be written this form, and the inverse matrix of A was 1 over determinant of A, scalar multiplication to adjoint matrix B, and it is its matrix multiplication to vector B. And if you consider the matrix multiplication, then it is adjoint matrix. I use JI because it is transpose matrix and BI. So it will give a linear combination as the entries GJ IBI. A summation. I will use summation. 1 to CNIBI, and it is same to 1 over determinant of A, and it is, if you use the same sense by changing the row, then it is, we can get the value of C1IBI as the changed matrix of A1, and similarly we get the determinant of AN. So it gives the entries, each vector of X is same to determinant of AI over determinant of A. I will skip the example, and in my note, the final point is, until now I skipped some theorem, and one is the triangular matrix. Triangular matrix's inverse matrix is also triangular matrix. That means rower triangular matrix is rower matrix. The inverse matrix is rower matrix. I will write rower triangular inverse matrix is also rower matrix. Rower triangular matrix, And in this sense, if we use the adjoint matrix, then the adjoint matrix will give upper triangular, adjoint matrix give lower triangular matrix. So from the fact A inverse is determinant of A adjoint of A. So since it is lower triangular matrix, so we get the fact that. And also, I skipped if the diagonal entry when the triangular matrix has all non-zero entries, then it will be invertible, and that fact comes from the fact that invertibility is if and only if the determinant of matrix is zero, non-zero.